You know that feeling, right? You snap a photo on your phone, you tap a filter, and boom, it just transforms instantly. It really does feel like magic. But what's actually happening behind that seamless split-second change? Well, it's this hidden world of just immense computational complexity. Today, we're going to pull back the curtain on Halide, the secret sauce that makes all of this magic actually possible. So let's get into it.
So think about an image like this one. When you apply a really nice filter, what's happening is that the software is performing a whole series of calculations on every single one of its millions of pixels. The fact that this process doesn't grind your phone to a halt for minutes or even hours is a truly monumental feat of engineering. The whole problem boils down to this. How in the world do you make millions of complex calculations feel completely instantaneous?
And this isn't just about making your photos look good for social media. High-speed image processing is the engine that drives so much of our modern world. We're talking about the camera in your pocket, the object detection in a self-driving car, even the cutting-edge medical imaging that saves lives. All of these things are in this constant race against time, and they all demand just extreme performance. Now, here's the thing. A single filter isn't just one operation. It's what's called a pipeline, a really long chain of interconnected steps. A professional-grade filter, something like the local Laplacian filter you'd find in Adobe software, can have close to 100 of these stages. And each stage depends on the results of the one before it, which creates this incredibly complex web of computations. Trying to optimize something like that by hand, it's a total nightmare.
And the stakes for getting this right are just unbelievably high. The difference between a simple, straightforward implementation and a highly optimized one isn't just a few percentage points. No. We're talking about something being 10 times faster, maybe even more. That's literally the difference between a filter that feels instant and an app that is completely, utterly unusable. So this all leads us to the core conflict, the central dilemma that programmers have been wrestling with for decades when they write this kind of high-performance code. And trust me, it's a fundamental problem with no easy answer. Let's break it down. Okay, so on one hand, you want what's called maximum parallelism. Your processor has multiple cores, right? So you want to split the work up and have it chugging away on as many pixels as possible, all at the same time. But on the other hand, you also want maximum data reuse, or locality. That means keeping the data you're currently working with in the processor's super fast cache memory, so you're not constantly making slow trips back to the main system memory. The huge problem is that these two goals are almost always fighting each other.
A simple blur filter is the perfect way to see this in action. It's a two-step process. First a horizontal blur, then a vertical blur. So what do? Do you compute the entire horizontal blur for the whole image first, save that huge intermediate image to memory, and then start the vertical blur? Well, that's great for parallelism, but it's awful for data reuse. Or do you compute just the tiny sliver of the horizontal blur that you need for each final pixel one at a time? Now that's fantastic for data reuse, but you end up recomputing the same values over and over and over again, which is incredibly wasteful. You see? Each strategy has a major pitfall. This whole collection of choices, the order of operations, where you store your data, how you group all the work together, this actually has a name. It's called the schedule. You can think of it as the master plan, the strategy for executing the algorithm. And getting the schedule right is the absolute undisputed key to unlocking performance. For years, programmers had to pick one of these flawed strategies and just bake it right into their code. This made the code super complex, really brittle, and totally locked into one specific kind of hardware. But what if you didn't have to choose? What if you could separate the recipe from the master plan for cooking it? And this right here brings us to the absolutely radical idea at the very heart of Halide. It's a complete rethinking of how we should write high-performance code. And there it is, straight from the source. The creators of Halide looked at this problem and said, let's raise the level of abstraction. They decided to decouple the algorithm, which is what you want to compute, from the schedule, which is how you want to compute it. And this is a really profound shift. So this whole what versus how thing, what does that actually look like in practice? Let's try an analogy to make it clearer.
Okay, think of the algorithm, the what, as the recipe for a cake. It tells you the ingredients and what the final cake should look like. Simple enough. Now, the schedule, the how, that's the chef's workflow in the kitchen. Are they going to premix all the dry ingredients first or mix everything as they go? How are they going to manage the oven time? You have one recipe, but you could have tons of possible workflows, tons of possible schedules, and each one has different trade-offs for speed and efficiency.
Halide lets you write the recipe just once, and then, completely separately, lets you try out any workflow you can possibly imagine. This separation just opens up a whole world of possibilities. You can tell Halide, hey, use a breath-first schedule, or no, try a total fusion schedule. Or you can get even more sophisticated and say, let's use a hybrid schedule like tiling, where we process the image in little chunks to get the best of both worlds. And the whole time, the core algorithm, the recipe itself, never ever changes. You're just swapping out the workflow. So what happens when you give a computer the power to not just execute a recipe, but to find the absolute best, most efficient workflow for any given kitchen? Well, the results are pretty staggering. You see, Halide comes with something called an auto-tuner. So instead of a human programmer trying to guess the best schedule, the auto-tuner just goes to work. It programmatically tries out millions of different combinations of strategies, tiling this way, fusing that way, parallelizing another way, and it measures the speed of every single one. It automatically searches this enormous space of possibilities to find the optimal schedule for your algorithm on your specific hardware. Okay, and the results? Well, they pretty much speak for themselves. I mean, look at this. In every single case, the code that Halide's auto-tuner came up with just blows away the code written by a human expert. We're talking more than 3 times faster on a CPU, over twice as fast on GPU. But then you get to the really complex stuff, like this local Laplacian filter. And the result there is, it's just staggering. Let's just pause on that for a second. 9 times faster. The code written by the expert probably took weeks, if not months, to write, and painstakingly optimized. The Halide auto-tuner found a better solution automatically, discovering performance strategies that were completely non-obvious to even the smartest human experts. But get this, it's not just faster, it's also dramatically simpler to write. The Halide code is just the recipe, the pure, clean description of the algorithm. And that code can be 5, 10, or in the case of the simple blur, almost 20 times shorter than the tangled, manually optimized mess it replaces. And this right here is why. On the left, you've got the clean, simple Halide algorithm. You can read it, you can understand it, it just describes the what. On the right is a metaphor for what it replaces. Hundreds, sometimes thousands of lines of convoluted, platform-specific code that's all manually managing the how. Halide just makes all of that complexity disappear. So, what's the big takeaway here? Decoupling the algorithm from the schedule is a genuine game changer. It lets programmers write simpler code that is not only way faster, but also portable. It can run on all different kinds of hardware, from CPUs to GPUs. It frees them up to be creative, to invent new algorithms, instead of spending months buried in manual optimization. And that is why Halide's DNA is inside the products you use every single day, from companies like Google and Adobe. And that really leaves us with a fascinating question to think about. We've seen what this idea did for image processing, but what other fields could be totally transformed by this? What new creative and scientific breakthroughs become possible when the smartest people in the world can focus purely on the what and just leave the how to the machine?